This is Jack Jackson. In this section, in this video, we're going to talk about tested proportions using a hypergeometric distribution. So the p-values will be computed from a hypergeometric distribution, actually using my hypergeometric function or formula for a TI, Inspire, or TI-84. Most inferential statistics situations involving proportions should, strictly speaking, use a hypergeometric distribution to compute probabilities. This is because the sampling is usually done without replacement from a finite population. Usually there is some finite population out there, and very rarely will we allow the same respondent or the same subject to be used twice in our sample. So that is a hypergeometric situation. However, if the population size is very large, then a hypergeometric distribution is approximated well by a binomial distribution. So we often use a binomial distribution instead of a hypergeometric distribution in this case because we do not have to know the large population size to use a binomial distribution. So it's very often that we can do that. If the population size is very large and the sample size is also large, a binomial distribution can be approximated by a normal distribution. So some people will use that, although honestly it is just as easy, at least for the p-values, to compute them using a binomial distribution as it is with a normal, and is much more accurate. So we'll get to working with binomial and normal approximations later, but in this video we're going to talk about the actual situation, which is a hypergeometric situation. If the population size is not large, then we must know the population size, and we must use a hypergeometric distribution to compute probabilities of proportions, because the binomial and normal approximations would not be close enough. So here's an example. Suppose that there is a set of 40 parts and it is claimed that the proportion of defective parts is 37.5%. We take a sample of 10 parts and find that one of them is defective. Do we have sufficient evidence to suggest that the true proportion of defective parts is less than claimed? Use an alpha level of 0.1. Well, we're just doing a p-value, and remember what a p-value is. It's a probability of getting something as extreme as what we actually got, or something more extreme. Okay, so we're doing less than, so this is a less than or left-tailed test, one-tailed on the left test, because it says we're testing to see if the defective parts is less than claimed. 1 out of 10 is 10%, which is certainly less than 37.5%. Okay, notice we're drawing from a finite population size, 40, and so we are talking about a hypergeometric distribution, and so we want to find the probability of getting 1 out of 10 or less in a sample of that size. So N, capital N, the population size is 40, little n, the sample size is 10. The null hypothesis is that their claim is valid, so the p-naught, or the proportion, true proportion in the population, is 37.5% or 0.375. Thus, the amount of successes, the number of successes in the population, is 0.375 times 40, which is 15. Of course, that needs to be a whole number, and of course it is here. The alternative hypothesis is that p-naught is less than 0.375, and thus m is less than 15. This is a left-tailed test. For our sample, we find x equals 1 defective parts, so the p-hat in our sample is 0.1, 1 over 10, x over n, 1 over 10, 0.1, 10%. But we're going to actually do the probability calculation with the x values. So we want to find the probability that x is 1 or less, well, 0 or 1 in this case, if we take a sample of size 10 from a hypergeometric distribution. Well, we know how to do this. So the p-value, once again, is the probability of getting a sample same as or more extreme than the sample we actually got. In this case, our sample, it had a p-hat of 0.1, which corresponds with an x value of 1. Here, more extreme means less than, since this is a left-tailed test. So the p-value is the probability that x is less than or equal to 1, which we compute using a hypergeometric distribution, where the population size is 40, the number of successes in the population is 15, the sample size is 10. Of course, we know that here's the formula for the PDF for a hypergeometric, and we want to sum that out from 0 to 1. But, of course, the good news is I have a program on my calculator, HGO-CDF, for a TI-84, and we can do that. You can actually do it with the summation if you set it up right in the TI-84 like this. And these screens over here, but if you've got my program that we went over back in Unit 2B, so if you'll go back to the slideshow for Unit 2, you can find the code for this program, and hopefully you already have that in. If you come to my office, I can hook up my calculator and give that to you. But anyway, we run that. We tell it the total population size is 40, the number of successes in the population is 15, the sample size is 10, and we want to go from a lower of 0 to an upper of 1 and find the probability between those inclusive, and it gives us an answer of 0.04. Here's the Excel command for the same thing. That's the same as the CDF right here if we make a CDF table. And that is the same as the area of these two bars from 1 to the left. That's our left-tailed probability, our left-tailed area. So, summarizing, capital N is 40 is the population size, little n is 10. The null hypothesis, their claim is valid, so P naught is 0.375 and thus M is 15. The alternative hypothesis is P naught is less than that, 0.375, so M is less than 15. It's a left-tailed test. Our sample had one defective part, which is a p-hat of 10%. The p-value is 0.04, which we can computed from a hypergeometric distribution. Since 0.04 is less than 0.05, which is the alpha level, there is enough evidence to reject the null hypothesis in favor of the alternative hypothesis. So there is enough evidence to say that the true proportion of defective items in the box is actually less than 37.5 that they claimed. All right, let's try another one. Maybe you could do this one on your own. Suppose that there's a set of 160 parts and it's claimed that the proportion of defective parts is 10%. We take a sample of 10 parts and find 3 of them are defective. Do we have sufficient evidence to suggest that the true proportion of defective parts is greater than claimed? Use an alpha of 0.1. See if you can do this one on your own. Press pause now. Well, hopefully you're able to do this. Hopefully you notice that the population size is 160. Since we know the population size and we're doing sampling without replacement, let's use a hypergeometric distribution to compute probabilities. The null hypothesis is that their claim is valid, so P naught, or the true proportion in the population, is 0.1, and thus M is 0.1 times 160. 10% of the 160 was 16. The alternative hypothesis is that P naught is greater than 10%, or equivalently M is greater than 16. This is a right-tailed test. For our sample, we find 3 defective parts, so that's a p-hat of 30%, but more importantly, it's 3 parts. So we want to see if we could get something that extreme or more. That extreme or more when we're doing a right-tailed test is 3 or higher. So there is the one way to do it with the with that, but we're going to do it this way with the program. It's by far the easiest way. Population size is 160. The number of successes in the population is 16. The sample size is 10. And then we want to go from 3 to 10, lower to upper, including 3 and 10, and add those probabilities up. So essentially in the PDF table, we're adding up these probabilities from 3 to 10, all the way from these right here. Or 1 minus adding the ones up here. But we actually did it by actually adding these up with the program, and it's 0.064. Graphically, it's this. Now these bars actually go all the way to 10, but some of them are too small to see. But we have a bunch of shaded bars here. 2 of them we can see, and there's some that are so small that we can't see them. Together, they have an area of, well, some of the y values, which in this case, since the bars are with 1, it's also an area, is 0.064. So look at this last bullet here. The p-value of 0.064 is less than 0.1, which is alpha. So we reject the null hypothesis in favor of the alternative hypothesis. There is sufficient evidence to suggest that the true proportion of defective parts is greater than 10%. Try another one. So example 3. Suppose that there's a population of 1,200 voters, and it's claimed that the proportion of voters supporting the president for re-election is 60%. We take a sample of 50 voters and find that 70% of them support the re-election of the president. Do we have sufficient evidence to suggest that the true proportion of voters supporting re-election is different than claimed? Use alpha as 0.1. Should probably try this one yourself, but here we go. The null hypothesis is that their claim is valid, so P naught is 0.6, and thus M is 0.6 times 1,200, which is 720. N is 1,200, or 1,200 is the population size. Little n is 50, which is the sample size. The alternative hypothesis is that P naught is not 0.6, thus M is not 720. Notice this not equal, so this is a two-tailed test. For our sample, we find P hat equals 0.7, so X equals 0.7 times 50, which is 35. Notice that has to be a whole number. Occasionally you'll see these and the percentages have been rounded off, the proportions or percentages have been rounded off, so you don't get a whole number here. Then what you need to do is round off your answer so that you always get X, both the N's and M all have to be whole numbers. And it's not really that you're rounding off X, it's the fact that they really rounded off the percentage, the P hat or the P naught. So anyway, we have X is 35, two-tailed sample. Now let's think about it a minute. 35, that was 70%. 70% is bigger than 60%. So something that value or more extreme would be 35 and up, or equally far on the left side. So we're going to find the probability that we go from 35 up, and we're going to double it. Okay. So the p-value is 2 times the probability that X is greater than or equal to 35. And so I ran my program over here. You can see the screenshots to the right. The population size is 1,200. The number of successes in the population is 720. The sample size is 50. And the interval of successes goes from a lower of 35 up to an upper of 50, which is the sample size. And that gives us 0.0908. So we want to take that number and double it, and that comes out to be 0.18. Well, 0.18 is greater than 0.1, which was alpha, so we do not reject the null hypothesis. There is not enough evidence to refute the claim of 60% in support of the presidential re-election. So that gives you at least 3 examples. We did a left-tailed, a right-tailed, and a two-tailed example of hypothesis testing using of proportions using a hypergeometric distribution. Then remember, this was the way you have to do it if the population size is small, and really we should probably always do it this way if we know the population size. In the next video, we'll see what we can do if we don't know the population size, but we know it's really big. Then we can use a binomial distribution instead.